Can you all confirm if you can hear me clearly, everyone? Okay, so I want to welcome you to another statistical learning class. Of course, today we're going to continue from where we stopped on Monday. The information that I'm actually going to be disseminating today, very, very crucial. In fact, very crucial to understanding the course. And I will advise that you should sit back and ask questions or where necessary. We talk about data and addition. Okay, I'm actually calling this data and addition part 2. Now, let me tell you this. Without data, okay, we will not be able to have something to train. Wait, okay, we may not be able to train our model, okay, without data. Without data, we cannot test how valid is our model. Without data, we cannot actually, test the performance of our model. And that is why data is very, very essential when it comes to, getting information. And let me tell you this. When data become available, that will drive our ambition. Please pay attention. Okay, pay attention. When data become available, okay, that will increase our curiosity. Okay, that will lead to more ambition. Okay, so data drive ambitions. Okay, now I'm not going to say this in general. Please pay attention. I'm going to say this in general. The statistical machine learning that we're talking about actually lies in the intersection of the data that we have and, the ambition that we want to achieve. Please pay attention. I see some people talking, but I need you to pay attention. This course requires your 100% attention. Okay, so this is what I'm trying to say. The statistical machine learning actually, lies in the intersection of two things: the data that we have and the ambition that we want to achieve. We actually want to fully achieve our ambition. So the statistical machine learning lies, in the intersection of the two. And let me now tell you this. When I talk about ambition, what do I mean? Ambition will drive some questions. Question like explanation, question like prediction, question like generalization. I'm going to say that again. Ambition will drive some questions. Questions like explanation. I told you the other time, we got some intention. Your intention is to maybe to explain, okay? Your intention may be to predict. Your intention may be to generalize. All of that are driven by ambitions. But the data, on the other hand, okay, actually, when I talk about the data set now that we have, the data set, on the other hand, now pose some constraints, okay? Pose some constraints, okay, and opportunities. The data set that we have poses some constraints and opportunity. Don't forget, I said ambition drives questions. Ambitions, okay, drives questions such as explaining, predicting, generalizing. But why data set that we have, okay, poses constraints and opportunity. But let me now tell you this. the true way forward. Some things need to come together. What is going to come together? I needed to pay attention now. What is the true way forward is the coming together of statistical theory, okay, computational tools, okay, and real world data. These three, they have to come together. And when they come together, they will be able to drive our ambition responsibly. Go ahead. Exactly. But before taking data at all, you have something in mind that you want to figure out. Exactly. Exactly. Upon seeing the data, I'm coming there now. Upon seeing the data, your ambition increases. Why? Because data has different nature. I want to talk about the nature of data now. Because the nature of data is very, very crucial. I'm actually going to say this. I'm going to write this now. Nature of data also matter. Number one, data can be structured. When I say structured, that is a regular data frame that you normally have, where you have numbers arranged in row and column. Has anybody seen a spreadsheet of data before? That's a structured one. We have unstructured one. Oh my God. The unstructured one will be image. You want to talk about image? You want to talk about speech? You want to maybe talk about genomic sequences and so on like that. Those are unstructured data. Your ambition is going to change, or there is possibility you need to update your ambition seeing the data. Does that make sense? Then we also have big data situation where the number of features, you got a lot of features with few numbers of observation or both sides. That's a big data. So the nature of data is actually very, very crucial. Please pay attention. If you don't understand, ask me question. Now, I'm going to say this again. Do you know why data poses constraints, challenges? You know why? Because the data could be noisy, could be incomplete, and could be biased. Please pay attention. Data could be noisy. When you are working with the noisy data, you need to be able to investigate whether it is noisy or not. We have an approach that we can use when your data set is noisy. Data could be incomplete. In this course, you're actually going to learn how to input incomplete data, because you know why? You may not be able to apply statistical methodology or machine learning algorithm when data are incomplete. Data could be missing. At times, you conduct survey, there's possibility you don't get a response. You don't get a feedback. And that kind of cell is going to be missing. How do we deal with that? Okay. And it could be bias. I talk about bias in this the way you collect your data. If you did not use what I call a principle of randomization, if you are biased in collecting your data, then your data is biased. Does that make sense? So statistics is like a story. Now, I think I just told you now the data and the ambition, and of course, what need to come together before we can actually drive our ambition responsibly. Okay, what we need to come together is number one, statistical theory. Number two, computational skill tools. When I say computational tools, okay, maybe we are actually talking about, because we're dealing with figures, we're going to compute. We need highly sophisticated tools to do that. And of course, the number three is the data itself. The three of them have to come together. And let me tell you this. This is an example of a structured data that I just talked about. Today, I'm actually going to walk you through some example of structured data and unstructured data, and then I'm also going to review the ambition that we're going to have. But let me tell you this: if your ambition is explanation, please pay attention. If your ambition is explanation, then you need interpretable models. I'm going to say that again. If your ambition is, okay, if your ambition is explanation, what do we mean by explanation? Why? Maybe you are asking a question. Why do variables relate? Why? Why do they relate? That is what we mean by explanation. Does that make sense? Then in that case, you do not need machine learning algorithm in that regard. You need interpretable models. Interpretable models can be found within statistical framework, like regression models, like graphical models that we're still going to talk about here. But if your ambition is prediction, you are not interested in why relationship occur. You are not interested, but you are focusing on predicting the future. Then the models that we normally use most of the times are black box models. Black box models like, has anybody heard about random forests? Thank you. Gradient boosting. Thank you. Deep neural network. Those models, thank you so much. Those models, they are very, very good when you want to attain huge predictive accuracy, but they are not interpretable. Okay, I want you to focus on this. We started now. This is a structured data. This is a structured data because we have a data frame, okay, where maybe in the row, each row represents cities in the United States, and each column represents crime variables. Now, if I have a data set like this, because there is no response variable, there is no label, then we're actually going to use unsupervised learning. Unsupervised learning here is just intention is maybe to categorize. Maybe our intention here, okay, our ambition here is, can we have a way to group cities with the same crime rate together, with a similar crime rate? And that is going to be the ambition here. Now, what is going to support the ambition? I told you the other time, there must be a coming together of statistical theory, okay, and computational tool. Now, the coming together will lead us to this, providing a graphical analysis, because we need to first start by trying to understand the variables in my data set. Then you know what I'm showcasing right now? I'm showcasing a scatter plot with density plot incorporated. Then I'm going to tell you the meaning of each of these. I'm begging you to pay attention, listen to me. The moment, if you don't understand any of this, ask me a question. Go ahead. Okay. Um, you're talking about the difference between the variables, right? Okay. Actually, if you take a look at all of these, there's going to be a description for each of that. So as time goes on in this course, that's a good question. If I have a variable, what is the meaning of the variable? Okay, I will tell you as time goes on. But right now, these are distinct offenses somebody can commit in cities. Does that make sense? Thank you. Now, what am I doing here? I want you to look at the diagonal. Please pay attention. Okay, pay attention. I'm taking this class to be a statistical party. If you are not enjoying my party, let me know. Does that make sense? Are you ready? You all ready? Okay, let's go. If you look at the diagonal represents the density plots of each crime variable. Why am I interested in density plots? I want to see the way they spread out. I want to see the way cities spread out in each variable. Okay, I want to see whether it follow normal distribution or there's possibility of outlier. I really want to see whether there's a particular city where they have extreme violent crime, so that I can send police to those cities to patrol the city. Does that make sense? I told you the other time, police don't just go out. They are statistically guided. So that is the essence of the diagonal. But when you go to off diagonal, please pay attention. When you go to off diagonal, okay, I mean it different things. In the off diagonal, I'm actually want to look at the relationship between any pair of crime variable. I want to see whether extreme crime variables like what is it called, like murder, like rape or robbery. I really want to see whether they are correlated. You know the meaning of that? I want to see whether they are correlated means in a particular city, if the event of murder is very high, does that necessarily translate into high occurrence of the other extreme, other crime event? That's what I mean. And let me tell you this: if the relationship is positive, then it means bringing that down, reducing the crime, which is the ambition of any society, bringing down the crime. Then they're going to use the same strategy for those variables that are correlated. Does that make sense? So the strategy that I'm actually going to use in reducing murder crime rate is the same that I'm going to use for the any other variable that are correlated. But when I take a look at it, the scalar plot, I realize that you know, property crime does not correlate with others. Now, how do I know? That I'm actually going to know from the scalar plot the relationship that they have. If it doesn't correlate, then if I want to bring the property crime down, then I need to use a different strategy. I'm going to use the same strategy for variables that are correlating. Does that make sense? Okay, that is exactly what I'm trying to say here. I want to go to another picture. What of in a situation? Please pay attention. Do you know that when I have a lot of variables, interpretation will be difficult to make? I'm going to say that again. When we have a lot of variables, interpretation will be very difficult to make. And you know what that means? Having a lot of variables actually means I have my data set in high dimension because that's a lot of variables. Therefore, I need a technique that will reduce the numbers of such variables. So what I'm going to do, I will artificially create two maybe lower dimensions. So the PC1 and the PC2 that you are actually seeing this course, we're going to talk about principal component analysis. The essence of principal component analysis is for dimensionality reduction. When I have high dimensional data, I have a lot of variables. Okay, it will be difficult for me to interpret variables in high dimensional space. And how can I reduce the dimension in such a way that I'm not going to lose a lot of information? Okay, then I can actually artificially create, lower dimension. And let me tell you this: when you take a look at this series at the data point, they are projected into this lower dimension, okay, putting into the consideration their principal component score. So in this class, we're going to have it, in a week, in 1 week, we're going to, dedicate a week for this principal component analysis. So what I'm doing right now, just to give you an overview of what you're going to be expecting. Does that make sense? Okay. Now let me tell you this. Hmm. What am I looking for? Do you know that where cities are clustered together, cities clustered together, you know what that means? Then it means they have very similar crime profiles. Go ahead. Not variables relating, not variables that we're talking about now. We're talking about cities. You know, cities are the data point, they are the observation. uh the variables are the crime variables. So what we're doing here, we are projecting cities into the two-dimensional space. Let me tell you this: the two-dimensional space, the PC1, the PC2, they are now representing the features, the crime variables. Because initially projecting cities in all the features would be cumbersome to interpret. And that is the reason why we create artificial variables, two variable, 2D, so that we can have interpretation very easy to make. Does that make sense? Okay. Now I want to come to this. Look at this. This is an unstructured data. Do you know what the ambition is going to be here? The ambition is to teach the machine learning algorithm to extract some features in this data set. What would be some features like digit 0 to 9 or alphabet A to Z? These are handwriting. Okay, somebody writes something down. At time when you visit a clinic, when doctor write prescription, at times I don't see their writing. So if I want machine learning algorithm to extract that, okay, so this is an example of unstructured data. So here, okay, and that was why I said here, okay, this is an image right now. This is an image. We could have thousands of images, but there's something I really want you to see. Please pay attention. There's something that I really want you to see. Okay, the images that I'm displaying right now is handwriting, right? Uma handwriting. Okay, and I want the machine learning to extract some hidden information. And let me tell you this: each image is in dimension. You can see that image is in dimension. Okay, now if I have an image that is 20 by 16 pixels, image contain pixels. So 20 by 16 pixels will actually means I have 330 quantitative variables. Now you know what is happening now. Okay, each image has 320 quantitative variables, and I'm actually going to refer to that as my data X. What will now be now, and another thing I'm going to talk about, each pixel actually has a zero, it's from a 0 to 255 intensity. Take a look at that. When I say intensity, I have a combination of white and black. Now, what is going to be my response variable? The response variable, it may be alphabet, because when you write something, it's either you write alphabet or you write digit. Now, how many possible digits do we have? We got 0 to 9, right? How many possible alphabet do we have? We have A to Z. What is the number of digits that we have 0 to 9? That would be 10. What would be what is the possible number of alphabet we have? That would be 26. Then what is the total now? That would be 26 plus 10. Then I got 36. Now my response variable here is the identity of the image, which could fall within the 09 digits or within A to Z. Does that make sense? Go ahead. Say that again. I'm not going to do just one simple image. There's going to be a lot of images. So each image has, of course, each image will have a dimension, and which is, if we have 20 by 16, then it means each image will have 320 pieces. Does it? This image, 320, another image, 320, all images have 320, and that 320 will be my X, my data X. Does that make sense? Okay. I used to be happy when students ask questions. So make sure you continue to ask questions. Okay, now what do you now think is going to be my intention in this here? My intention is now going to be I'm going to be solving a classification problem. I will use the model. I will build my model on the data X. Okay, data X in this case is actually the dimension of each image, the 320 categorical variables. Then I want to classify. I want to make a prediction. Okay, I really want to learn about the identity of what is written down. That is the ambition here. Does that make sense? And in this case, we actually going to in order to unravel the identity, we're going to train our data. And when we train our data, we're going to test. Because the only way we're going to know whether our model is doing a great job is when the model do a great job on training data and also do a great job on the test data. Does that make sense? That's exactly what I mean. Now I want to move right now. If you take a look at what I'm seeing, what I'm showing you now, this is what we call heat map of DNA microarray data. Now let me tell you this. When you take a look at this picture here, you're actually going to see three different colors. Okay, you're actually going to see red, you're going to see green, you're going to see black. Please pay attention. This, we want to talk about gene expression. In a gene expression, in the data frame is going to be structured. The data frame is going to be structured. The row in the data set is going to be gene, while the column is going to be samples of genes. The samples of genes that you collect from patients. And let me tell you this, if I produce an heat map, okay, color red here means gene with high expression. Color red means gene with high expression. Color green means gene with low expression. And color black is a benchmark, a baseline. Does that make sense? So this is an heat map. Okay. If you take a look at this very heat map right now, the heat map, the color, different colors will tell us a different gene expression, because what we want to do, we actually want to classify genes, okay, genes that belong to the same category. We also want to classify samples, and with the heat map, we will be able to know that. But let me tell you this, uh, if I really want to know the intensity of the relationship among genes, depends on whether the color is dark or light. Whether the color is dark. When the color is dark, that is high intensity, high correlation. High correlation means the genes are similar. Does that make sense? And when it is light, okay, when it is light, then it means the similarity is very high. They should not be in the same category. Does that make sense? And that's exactly what we mean. Now, if you take a look at this, the one here, we call that dendrogram. We're still gonna, I think our next, probably next week, we're gonna start what we call clustering. Okay, in clustering, we're gonna use a dendrogram. We use this dendrogram is like a tree structure. We're actually gonna use that in, in classified objects into different groups. Okay, so pay attention. Now I'm actually moving. Okay, so I just talked about the clustering. Okay, all right. Which one is on structure? Oh, no, this is going to be structure. So from the structure we produce okay. Okay. Now what can one learn from expression data? Okay, gene expression data. I told you using the heat map, you will be able to determine using the color. When the color is red, that is high expression. When the color is green, low expression. When the color is black, okay, that is like a baseline. Okay, now if you are asking a supervised question, then you actually want to see which type of tumor, okay, can be predicted from a gene expression. If I have this particular gene expression, what type of tumor can be predicted from that? That would be a classification problem. Does that make sense? Or we could be asking question, which genes are more predictive for which tumors? And that is why we're talking about this. Now I want to move right now. Now this is what we call correlation matrix. What you are seeing now, please pay attention. This is what we call correlation matrix. Now we got this from structured data where we have genes against samples. We have 62 samples of genes. I mean, take a look at that. 62 lymphoma samples. And each of these samples has more than 4,000 gene expression. I'm going to say that again. Sample that you get from the individual, okay, could have thousands of expression of gene. Okay, so now because I have 62 samples, I can actually generate a plot 62 by 62 correlation plot. And let me now tell you this. The essence of doing 62 by 62 plot is to see how these lymphoma samples are related. When they are related, we can classify them into the same group. If they are not related, they automatically they become different groups. And if I really want to know the intensity of the relationship, then I'm going to focus on, is it dark or light? If it is dark, the relationship is strong. They should be in the same group. If it is, dark means correlation very close to 1. Light means correlation close to 0 or negative. That's what we mean here. I'm going to say that again. Dark, correlation close to 1. Then light, correlation close to 0 or negative. This is also an heat map. But let me tell you this. Do you know that? Imagine I have 62 by 62. What if I have 1,000 by 1,000? It will be difficult to use colors to make a decision. That could be misleading. We could be overwhelmed. And because of that, we normally use what I call distance-based representation. In this course, I'm actually going to walk you through multi-dimensional scaling. The multidimensional scaling enable us to investigate the trend, the relationship among so many variables. Because using heat map, the heat map based on colors with so many variables, you'll be overwhelmed. You may not be able to interpret heat map correctly. And because of that, instead of us to be working with correlation, we are no longer going to work with correlation. We're going to be working with distance. Does that make sense? Okay, now what we're going to do, please pay attention. Take a look at this. I'm actually going to artificially create two dimensions. The same way that I did under principal component analysis the other time. I'm going to artificially create two dimensions. Okay, the two dimension, then I'm now going to project variable, the data point in the high dimension to the low dimension. Okay, when I do that, they're using it in such a way that the distance among them will be preserved. But you may not be able to see the distance clearly using the heat map. But you'll be able to do that using the multidimensional scaling. Okay, so that's exactly what I mean. Okay, now I said something the other time. Go ahead. Okay, you mean how to interpret this one? Take a look at this guy. Because they are clustered together, they're going to be in the same category. If you take a look at, you can see numbers here, right? That should be 62. We're talking about the sample, the former samples. Okay, they are 62 in number. Now, based on, and each of them has gene expression. But using the heat map, you are not able to categorize them because you're going to be overwhelmed. Okay, we make use of colors in heat map. We now want to make use of multi-dimensional scaling. Okay, we want to create artificial dimension. Okay, the MD1 and the MD2, the artificial dimension. Then we know what we're going to do. We're going to project the 62 samples into this dimensional space. So it's like we are projecting 62 samples that are from higher dimensional space to lower dimensional space. Why are we projecting them to lower dimensional space? For easy clustering. Right now, I'll be able to know that the genes here, they are related. They should be in the same group. The gene here is far from the one here. They are not related. Does that make sense? Because we may want to classify genes into categories so that we'll be able to say, okay, this particular set of genes, these samples of genes, okay, they are the ones that are responsible for this, maybe the growth of a tumor. Does that make sense? So that's what I mean. Now, I remember I said something the other time that data may be incomplete. Okay, take a look at this. There's something that we call moving rating. We're still going to do this as a topic in this class, where we call it missing value imputation. Okay, you have a data frame, a structured data, but some values are missing. But let me tell you this. There was a time Netflix actually introduced a competition. Has anybody heard about that competition before? Okay, in that competition, they asked their customers to rate some movies. And you're going to see here where you have a word, when you have that guy, that data is missing because Tom did not watch that movie. How do you expect me to rate a movie that I did not watch? Then in that situation, that particular space will be declared missing. And if I want to perform any statistical analysis with this particular data set, the fact that I have an incomplete data set, there's going to be an issue. Therefore, I should have a way to complete that, to impute that. So one of the topics that we're going to be doing in this course is going to talk about missing value imputation. Does that make sense? Okay. So that is what you have. Now, you know, the challenges for recommender system, data are extremely high volume, like 1 million to 1 billion rating. Imagine the subscribers, the number of subscribers our necklace have. And we need to, and that is extremely sparse. You know what we mean by extremely sparse? There's going to be some sales without rating because the fact that customer do not watch that movie. Okay, that's why we say extremely sparse. Okay, and of course, you see the users 71,560 over 10,681 movies. Look at that. And of course, the observed rating is about 10 million. And the rating, that was the rating out of 764 million. That is extremely sparse. Okay, which this has 1% observation rate. There's going to be a lot of incomplete. And if you want to bring out a meaningful information from this, okay, statistical model requires a complete data. Therefore, you need to be able to use, to be able to compute that. I'm going to walk you through that in this course. What about collaboration, relations between statisticians? We live in a, this world is a global village because of the interactions, because of the collaborations among experts, among friends, among individuals. Because of that, we're forming a community. Okay, now do you know we're actually going to talk about this in graph mining, in graph model used by Facebook. If somebody posts, okay, if somebody have a post on Facebook, okay, and you comment or you like, okay, then the Facebook now have it in mind that you like that very content, and they actually going to classify you into a particular group. So how we do that? And that will be through, graph mining. So in this class, I'm actually going to walk you through community. We call that, how do we detect community? Because if I put a post on Instagram or I put a post on Facebook or on TikTok, and if you press like, then I'm going to be encouraged. And when I'm encouraged, then I'm building community. So we have a way to detect that. The Facebook owner, the Instagram owner, the TikTok owner, with the click that you have, they're making more money. Okay? So we actually, and that was why I call that community detection problem, where we introduce statistical model for the network to motivate effective algorithm. Okay, so that is graph mining. Okay, before I go, I want to have a good quote to keep in mind. Please pay attention. Essentially, all models are wrong, but some are useful, according to George Box. But how can you make them useful? Let me tell you, why do you think he said models are wrong? He said models are wrong because model does not give an exact characterization of reality. There's always going to be a gap. Whether you use statistical model or you use machine learning algorithm, there's always going to be a gap. But you know what? We acknowledge that, but we want to minimize gap. And the only way to minimize gap is for you to be able to recognize your ambition, to be able to make a good choice of statistical model and the machine learning algorithm. And lastly, there is no interpretation of anything. Interpretation is a vehicle in the service of human comprehension. A vehicle in the service of human comprehension. The value of interpretation is in is in enabling others to, fruitfully think about an idea. I'm challenging you today. Think about an idea. You have a valuable idea in you. You have what is going to make the world to actually be in a better place. Say it out. Discover the idea. Okay, and this quote is actually from ST et al. 2009. This is what I have for you today. I want to believe. Do you enjoy my statistical party? Okay, see you on Friday.